Right now, deep within the Earth and beyond the stars, two of humanity's greatest scientific achievements, the James Webb Space Telescope and the Large Hadron Collider at CERN, are revealing a cosmic riddle that questions our entire universe theory. The James Webb Space Telescope searches the faraway universe for hints of antimatter's presence in space, whereas the LHC studies and creates antimatter by smashing particles together underground. Their joint endeavors aim to address a fundamental puzzle in physics. Since our current understanding of the rules of nature implies that there ought to be an equal quantity of antimatter, why is our world primarily composed of matter? From the tiniest particles that humans have discovered so far to the largest as-yet-undiscovered regions of space, this collaborative effort covers it all. Not only are revolutionary experiments being conducted at CERN to create antimatter, but they are also carefully studying its behavior in relation to matter. At the same time as it aims toward the edge of the observable universe, Webb is searching for anomalies that might point to areas where antimatter is dominant, a quest that has the potential to shake up decades of scientific agreement. Their potential findings might have far-reaching consequences. In addition to casting doubt on the widely held Big Bang theory, this finding may herald the arrival of hitherto unseen cosmic domains dominated by antimatter. These kinds of findings have the potential to usher in game-changing technology, such the ability to use antimatter as a power source or even as a connecting factor between stars for future space travel. These keepers of human knowledge silently watch as humanity teeters on the brink of changing the rules of the universe. Currently, a long-lived mystery is being unraveled by the combined efforts of CERN's particle physicists and Webb's unmatched view of the universe. The fact that matter predominates over antimatter in the universe is more than just a mystery. It's the driving force behind our existence. Deciphering this secret could represent a monumental leap forward in our pursuit of cosmic understanding. The seeming disparity between the quantities of matter and antimatter in the universe is the central conundrum at the heart of particle physics and cosmology. Current theories propose that matter and antimatter were both created at the same rate during the Big Bang, but the universe as we can see it now shows that matter is far more abundant than antimatter. Then we have to wonder, what happened to the antimatter? And why is matter so powerful? In an effort to unravel this riddle, CERN is conducting controlled experiments with antimatter through high-energy collisions, which briefly recreate conditions similar to those immediately following the Big Bang. The goal of these investigations is to find out how the cosmic imbalance came to be by detecting any subtle changes in the behavior of matter and antimatter. At the same time, this search is expanded into space by Webb, which has unmatched observational capabilities. From a cosmic viewpoint, it searches for gamma rays and other signals that might point to areas where antimatter is destroying matter. In an effort to comprehend one of the universe's greatest mysteries, this twin strategy merges the accuracy of particle physics with the scope of cosmic observation. This mystery calls into question our most basic assumptions about the nature of the cosmos and how it has evolved through time. An explanation for the imbalance would have far-reaching consequences for our understanding of the universe's basic rules, as it would clarify new physics beyond what is currently known. Problems ranging from the microscopic realm of subatomic particles to the enormous cosmic expanse necessitate a multi-pronged strategy. How can we go out on a mission to unravel a riddle of this magnitude? In the state-of-the-art labs of CERN, where antimatter is being studied in groundbreaking ways, the first parts of this cosmic jigsaw are being assembled. In the middle of Europe, researchers are crafting new understandings by simulating and studying conditions just a few microseconds after the Big Bang, with the help of the biggest and most complicated scientific apparatus in the world. We are not merely venturing into the cosmos's subterranean domains, we are entering the future of scientific discovery as we do so. The most cutting-edge antimatter experiments are housed at CERN, the European Organization for Nuclear Research, which is tucked away beneath the Swiss-French border close to Geneva. In an unprecedented endeavor, physicists are harnessing the might of the Large Hadron Collider, the most massive and powerful particle accelerator in the world, to create, collect, and analyze antimatter in a setting reminiscent of the early cosmos. Achieving this accomplishment requires subjecting particles to accelerations close to the speed of light, followed by collisions that generate observable quantities of antimatter particles like positrons and antiprotons. Antimatter research facilities at CERN, such as the antiproton decelerator and the alpha and ATRAP experiments, are leading the way in understanding the nuances that distinguish matter from antimatter. The exact nature of antimatter particles' interactions with matter, electromagnetic fields, and gravity is a topic of intense study. Examining the possibility of antiparticle and particle decay asymmetry is a primary goal, since it may explain the apparent matter-antimatter imbalance in the cosmos. To enable scientists to study antimatter for long durations, the experimental setup at CERN comprises of complex cooling processes and trapping devices. This capacity is fundamental for measuring antimatter's properties precisely and comparing them to matter's. Examining these comparisons, CERN researchers hope to find any small differences that could explain why matter was more abundant than antimatter after the Big Bang. Future technologies, such as antimatter propulsion and possible energy sources, stand to benefit from CERN's antimatter research, which aims to explain why the cosmos mostly persists in its present form. An important clue to cosmic asymmetry and the rules that govern our world can be found in the groundbreaking antimatter research that has been conducted at this facility. The riddle of matter's predominance in the universe becomes even more complex as antimatter is suddenly harnessed within the limits of CERN's ultra-modern laboratories. The search for knowledge, however, shows no signs of stopping, and it has already expanded beyond the little sphere of particle accelerators on Earth and into the enormous cosmic arena. Stationed in the frozen wasteland of space, the James Webb Space Telescope is prepared to assume responsibility for this intergalactic inquiry. With its state-of-the-art observational capabilities, Webb might potentially find the faint traces of antimatter floating around in space, assuming such a thing exists. We are on the verge of maybe solving one of the most baffling puzzles encountered by contemporary science as we shift our focus from particle collisions in CERN's subterranean facilities to the astronomical observations that the Webb will capture. James Webb Space Telescope, situated 1 million miles from Earth, is ready to reveal the secrets of the cosmos with its complex sensors. Webb is able to see beyond cosmic dust clouds and into the secret worlds of faraway galaxies because it is extremely sensitive to infrared light, unlike its forerunners. With this cutting-edge capabilities, Webb sets out on an unrelenting mission to detect the tiniest hints of light from the universe, painstakingly surveying the enormous expanse of space for any anomalies from the predicted patterns. With its pinpoint accuracy, Webb searches for minute discrepancies that could reveal the existence of antimatter concealed in the fabric of space and time. The goal of Webb is to detect signs of antimatter interactions or annihilations by analyzing the spectra of faraway astronomical objects. If these nebulous hints could be located, they might shed light on the cosmic scale distribution, abundance, and behavior of antimatter. There is more to Webb's cosmic observations than only the detection of antimatter. While doing so, it hopes to illuminate the processes that control the birth and development of stars, galaxies, and planetary systems, as well as the underlying mechanics that drive the cosmic symphony. Our cosmic existence is being shaped by fundamental forces, and the secrets of the universe's composition, dynamics, and beginnings may be revealed as Webb's sharp eyes scan the depths of space. The unfathomable depths of the cosmos remain shrouded in mystery, but the James Webb Space Telescope is prepared to shed light on them. The vast disparity between matter and antimatter, however, remains a basic conundrum in the vastness of space. While Webb searches the universe for faint signs of antimatter, this cosmic imbalance sends shockwaves through space-time. The discrepancy between matter and antimatter has significant consequences for how we interpret the structure, history, and ultimate destiny of the cosmos. The universe should be empty of both matter and antimatter by now if they were both formed at the same rate in the early universe. However, they have since destroyed each other. On the other hand, matter seems to have won the cosmic war, with antimatter confined to a mysterious fringe existence. Beyond basic cosmic curiosity, this discrepancy raises fundamental issues regarding the very basis of reality. From the birth of stars and galaxies to the origins of life, The mysteries of the cosmos can be solved by deciphering the rules that govern the predominance of matter over antimatter. In addition, the cosmic structures that control the evolution of the universe over billions of years are impacted by the imbalance between matter and antimatter, which in turn dictates our cosmic destiny. The results of Webb's incessant search for antimatter will have consequences that extend well beyond the field of astrophysics. Our basic knowledge of particle physics, cosmology, and reality itself is called into question by the matter-antimatter imbalance. It forces us to be humble and curious as we face the mysteries of the universe, a reminder that the universe is more complex and amazing than anything we can fathom. In light of these profound mysteries, the hopeful light of Webb's watchful eye illuminates the deep recesses of space, holding the potential for new discoveries. In our shared thirst for knowledge, we set out on an adventure into the unknown, hoping to one day understand the universe for what it really is. So, come along as we investigate the cosmic mystery that underpins our very being by delving more into the consequences of the matter-antimatter asymmetry. Realizing that matter predominates over antimatter goes beyond basic scientific inquiry. It questions the very foundations of the cosmos and our place in it. This colossal mystery spans the universe, from the tiniest scales to the farthest distances, linking the vast domain of particle physics with the microscopic expanses of space. The main question that arises from the matter-antimatter imbalance is how we can explain the behavior of the cosmos based on our current knowledge. It delves into the processes that govern the evolution of the universe from its early stages to its current structure, compelling us to face the fine line between symmetry and asymmetry in the universe. The consequences of the matter-antimatter problem for our place in the universe are enormous. If there had been an equal amount of matter and antimatter in the universe, its mutual destruction would have resulted in a dead, sterile world without the intricacies we see today. Instead, matter is so abundant that it serves as a rich soil for the growth of galaxies, stars, planets, and life. The more we investigate the matter-antimatter asymmetry, the more we learn, and these revelations have cosmic ramifications. Antimatter is a pervasive mystery that begs us to solve it and learn more about the universe, from the delicate tango of subatomic particles in particle accelerators, like the Large Hadron Collider at CERN, to the cosmic waltz of galaxies and black holes seen through telescopes like the James Webb Space Telescope. Although their observational scales are very different, CERN and Webb are complementing scientific institutions that are helping to solve the matter-antimatter conundrum in their own unique ways. At CERN, researchers explore the subatomic world by producing and studying antimatter in a controlled setting using particle accelerators. They probe the basic physics that control antimatter's interactions with matter and reveal its complex behaviors and properties through painstaking investigation. On a grander scale, the James Webb Space Telescope surveys the cosmos for hints of faraway galaxies and other astronomical events. To learn more about the distribution and evolution of antimatter in the universe, its sharp eyes search the cosmos for abnormalities and subtle signs that might reveal its presence on a cosmic scale. The collaboration between CERN and Webb is mutually beneficial, connecting the cosmic with the tiny. Together, they cover a vast expanse of time, from the first moments of creation all the way to the intricate dance between matter and antimatter that formed our modern cosmos. Their combined knowledge sheds light on the origins of the universe, its demise, and the basic imbalance that allowed galaxies, stars, planets, and life to form. Discovering the presence of antimatter in space would be a game-changer for our understanding of the cosmos, and the James Webb Space Telescope is poised to make that happen. An extraordinary leap in our comprehension of the universe would result from such a finding, which would also confirm the theoretical foundations laid by CERN's antimatter experiments. Just think of the consequences. The findings from Webb could throw a wrench into our current notion of the universe's makeup by exposing pockets of antimatter hidden within the galaxies. Scientists would then be able to interpret the cosmic fingerprints left behind by these mysterious particles, thanks to CERN's painstaking investigations on the behavior of antimatter in controlled laboratory conditions, which would serve as an essential reference point. New insights into the universe's building elements may be revealed as a result of this merging of particle physics and astrophysics, two seemingly unrelated fields of study. Potentially, it could provide light on long-lived mysteries such as how matter came to be, what cosmic structures are made of, and what happens to the universe after this. The complementary work of CERN and Webb further demonstrates how science is inherently a collaborative endeavor. Researchers stand to gain fresh insights into the universe if they can successfully combine data from space with studies conducted on Earth. Essentially, the possible finding of antimatter traces in space is a watershed moment in scientific history, opening the door to a more profound comprehension of the cosmos and our role in it. It encourages us to think about the deep secrets that exist beyond our present understanding and to venture into the unknown realms of cosmic occurrences. Beyond the domain of science, the exploration of antimatter brings up deep philosophical and ethical questions. Investigating the matter-antimatter asymmetry makes us wonder where the cosmos came from and what will happen to it. CERN's particle collider investigations into antimatter challenge our most basic assumptions about the nature of the universe. Just as our understanding of our place in the universe is being tested by the James Webb Space Telescope's astronomical observations, our understanding of the universe as a whole is being tested by the same mission. Antimatter signatures could have far-reaching consequences, leading us to wonder where we fit into the grand scheme of things. Is our function in the cosmos more than just that of an observer in a vast cosmic drama? These philosophical and ethical questions make us reevaluate our place in the universe and the far-reaching consequences of our pursuit of knowledge. The intricate relationship between finding out more, comprehending more, and carrying out our ethical duties in seeking the truth is a challenge as we continue to expand the frontiers of scientific inquiry. Collaborating with the James Webb Space Telescope, which is still exploring space for its hidden secrets, and CERN, which is determined to understand the universe's building blocks through particle physics, could solve the mystery of antimatter. We get closer to solving the long-lived riddles with each astronomical observation made by the JWST, an experiment performed at CERN's cutting-edge facilities. Their work may, in the end, offer light on the mysterious properties of antimatter and its impact on the universe. This never-ending campaign does double duty. It deepens our understanding of the world and serves as a constant reminder of the boundless curiosity and dogged persistence that drive scientific progress. We are excited about what the future holds because we know that there will be revolutionary breakthroughs soon. We are witnessing the peak of human curiosity and inventiveness as the James Webb Space Telescope's far-reaching observations meet the revolutionary antimatter experiments at CERN, calling all those who are enchanted by the secrets of the cosmos. We are on the verge of making discoveries that could change the world. Come with us on this incredible adventure as we explore the cosmos and the microscopic world of particles. Let us work together to solve the mysteries that have baffled people for ages. If you want to know what's happening in the world of cutting-edge astronomy and physics, subscribe to our updates. We can discover the universe's hidden mysteries and expand the limits of human understanding if you help us. Joined in this shared pursuit of knowledge, we set out on an adventure into the unknown, ready to discover the deep secrets that will mold our view of the cosmos. What do you think of this? Let us know in the comments. Since you've watched this video until the end, we have another interesting video for you. Click on the video on your screen after subscribing on us, of course. See you in the next one.